Hi, I'm Adolph Oliver, and this is the first of a number of video clips that we'll be looking at dealing with systems of equations. Now, what's really going on here is this. Now, the thing that's the most effort usually in a word problem is getting the equation correct from the words. After that, the solution is not difficult. Well, in many word problems, it turns out that it's easier, instead of using one equation, to set up two, for instance, like we see right here. This is known as a system, and each one of them contains part of the information of the problem. If you can solve them together, then you get the solution for the whole problem, and that's often easier than trying to set it up with just a single variable. Here we've got both an x and a y, for instance. So here's what we're going to do. By the way, the form that these can be in varies. This first one up here is what we call standard form again. The x and y on the left, plain number on the right. This second guy here is in slope-intercept form. Y equals mx plus b. Okay, they can be in any of the standard forms or any of the forms that you deal with in grafting. And of course, what's going to happen is you're going to get a good chance to practice your graphing again here. Anyway, what's important to do is to understand what's going on in the solution process when you have a system of equations like we just showed you, for instance. And that's why we always draw pictures to begin with and do the grafting so you can see what's going on. Now, grafting, we're not going to knock ourselves out being super accurate here. So you're not going to be able to get the answers right on the button perfectly. You'll come close, but there's no reason to worry about that because there are two algebraic methods, substitution and elimination, that we'll be looking at, that allow us to get the answers exactly. But what we need to do is understand what is going on. So here we go. If you've got two equations, like the ones we showed you up here, and you graph both of them on the same xy axis, there are three different things that can happen. The two lines that you get, one from each of the equations, can be parallel to each other. Now, if they're parallel, of course, this means they do not cross, okay? And if they do not cross, then there is no a common solution. So if they don't cross, the answer on this is no solution. Now, here's another thing that can happen. The two equations can be on top of each other. You plot the first one, here it is. You plot the second, and it's right on top. That means, of course, they're both the same equations. And what happens here, they cross their entire length. Okay. Well, what happens here is you don't have one solution. You've got an unlimited number. Any point on here, the xy value on this is a solution. So we can say what we have here is then infinite solutions. Okay, so let's write that down here. Infinite and unlimited number of solutions. Okay. Now, here's the first thing we want to say about these two that we've just talked about. These two do not happen in real problems. Okay, if you have a real problem and you get parallel lines or lines on top of each other, then you know what you do is you have a bad solution. I'm going to just say these two guys are the bad ones. Now, the first thing, of course, is you say, well, why in the devil are we learning things that shouldn't happen? Well, for a very good reason. Because we want to catch mistakes we make when we work in solving problems. And if you ever get parallel lines are on top of each other in a real problem, you've definitely made a mistake in your equations. You better go back and work on it. So in math, it's very important to know when you're wrong as well as when you're right, so you can go back and fix it up. Now, the guy in the end here, where the two lines cross, this is what happens in real problems. Okay. Each one of the equations contains some of the information about the problem, and the point where they cross right here is the solution that's common to both, and it is the system solution. So what happens, they cross in one point, okay, and that one point is the problem solution. Okay, well, let's take a little more look at this and see what's going on, because we'll want to be able to tell when we're bumping into these guys in the future. Remember, you should always have lines across like this if you've got the correct equations for a problem. If you get the lines on top of each other or parallel, you definitely have made a mistake, because they don't cross. There's no solution in parallel. You don't have an answer at all. And the on top of case is even worse. You've got an unlimited number of answers. Well, let's take a look at what's going on here. You see the parallel case? The lines do not cross. So what the parallel case means is these guys have the same slope. But notice now that their y-intercept points, where they cross the y-axis, okay, these spots, they have different, okay, y-intercepts. Okay, let's take a look at the next one here, our on top of case. The on top of case, again, well, obviously they got the same slope because they're on top of each other. So we got same slope, but now notice something else is the same. They both have the same y-intercept. Okay. Now you're wondering, where in the devil am I going with this? Well, here we go. The punchline is coming up real quick. Go over here and look at what should happen in a real problem where the lines cross. You don't have to worry about the y-intercepts. You simply say one thing. They have different slopes. And if they have different slopes, sooner or later they're going to cross someplace, and that's going to be your system solution. So here's another way to tell bad cases. If you have a bad case, the equations, are either parallel or on top of each other, they're going to have the same slope. Okay, these two guys are the same slope, and the two on top of each other here are the same slope. How do you tell between the parallel and the on top of case? Well, you look at the y-intercepts. If the y-intercepts are different, then the lines are not on top of each other. You got the parallel line case. If the y-intercepts are the same, then they're definitely on top of each other. You've got the same equations here. And of course, again, how do we tell the case here that happens in real problems? Simply different slopes right here. You got different slopes. Sooner or later, they're going to cross. Okay, well, the algebraic methods that we're going to be using to nail down the answers on these, because we're just going to make the graphs rough here to see what's going on. But the algebraic methods will allow us to get the answers exactly, but we want to know what's going on, because this parallel and on top of case, the bad ones, can occur. Their property of the equations. You'll have a bad case whether you graph it or whether you use the algebraic methods, substitution, elimination. It's a property of the equations and not the method that you're solving. So we want to be familiar with how this can work. Well, let's take a look at some examples here. Basically, what you're doing here is you're getting practice on your graphing again. And of course, you'll be seeing more grafting as we go on. So we got a big XY grid right here, and here are the two equations. Now remember, there are different methods to be able to graph these guys, and those methods are table of values, the intercepts method, and the slope-intercept method. You can use any one of those three methods on any of these individual equations. You don't have to use the same method on both of these guys here. You can do one way and another way. The thing, of course, is just get them grafted correctly. Well, if you've got the equations in the y equals form like we happen to have here, then the easiest thing to do, since they already match up perfectly with slope-intercept, remember that's y equals mx plus b. Okay, the coefficient in front of the x is the slope. The letter m stands for slope. And the b is the y-intercept. So I'm going to call this my equation number 1 and my equation number 2, because I'm going to graph them both here. And so here's the information on this. Equation number 1, the coefficient in front of the x is -2. So m equals -2. Okay, the b is simply +4. Okay, well, remember the b is the y-intercept. So where is this guy going to start? Well, okay, here's y equals +4 right there. I just made a dot on it, counted 4 up. Now, the slope m, remember that's rise over run. So here's what we're going to do with this. M, which equals rise over run. This is the old engineering terms for it. Okay, I'm going to make a fraction out of this guy by putting a 1 underneath. And if he's got a negative, I always like to take the negative upstairs. So I can write this as -2 over 1. And that, of course, equals the m equals -2. Well, remember, why we say rise over run is this allows us to then identify who's the run and who's the rise. I always like to do the run first. Remember, I only run horizontally. So the run is in the x direction. And from our starting point right here, the y-intercept, which was +4, the run is going to be 1. So I go to the right one. This is where we use the arrows like this. So here it is. Run equals +1. Now, we do the rise from the end of that arrow. So we got to go down 2. So here we go. Down 1, down 2, right there. So there's the rise equals -2. Well, at the end of that second arrow right here is another point that's on the line. So what you do is you get out your ruler here and simply connect up the dots here. Here it is, about like that. And that's my equation number 1. Okay, notice the second guy is also in the y equals form. So when they're in the y equals form, y equals mx plus b is the easiest thing to use because it matches up directly. Okay, here we go. The m is the coefficient of in front of the x here. So m in this problem equals -1/4. Now we're going to do the rise and run in that in a moment. But we first have to have our starting point. So what's the b for this guy? -3. So let's go down here. 1, 2, oops, 1, 2, -3 would be right here. Okay. Now, we're going to go a slope of -1/4. Okay, let's write it over here where I got a little bit more room. M equals, of course, rise over run. Okay, here we go. And in this particular case, we've got -1/4. Well, I'm going to take the minus upstairs again. And so here it is. The rise is the guy on top, -1. The run is the guy on the bottom. So here we go. Starting from our y-intercept point on this second equation, I'm going to run 4. +4 is 4 to the right. 1, 2, 3, 4. So it's going to run right to this point here. And then it's going to go down 1. Remember, that's our run here. Run equals 4. And then we go down 1. That's our rise. Okay, so the rise equals -1. That's this guy. Okay, well, here we go. Once we get this set, Okay, we run 4 and we went down -1 and rise. Then we get our ruler out and connect up the dots here. Let's see if I can do it fairly well. Here it is. This is equation number 2. Well, if I extend equation number 1 here, somewhere in this area right here is where the two of them cross. And this is the system solution. Now again, I haven't knocked myself out being super accurate here. But you know, if you took a stab at this, it might be something like x equals 6 and y equals -5. I don't expect that to be the exact solution. It'll be somewhere around that particular solution right there. So this is the idea again. What you're going to have here is a system of equations, and we're doing the simplest thing, just 2 equations. We're going to graph them both on the same xy plot. And so since these are both in the y equals form, it's easy. It's just use y equals mx plus b because everything's exactly the way we want it. We just read off the values. The slope equals -2 and the b-intercept plus 4. That's what we use to graph to line number 1. Line number 2, the slope is -1/4 and the b value is -3. So I started at -3 and then stepped off the rise and the run. The run was +4, the rise was -1. Drew the second line. Somewhere down in this area right here is where they're going to cross. Again, we're not worried about being super accurate here because we can get the values exactly using one of the algebraic methods. But one thing we know is that they do cross, so there is a good system solution for this particular problem. Okay, let's take a look at another one here. Okay, here we go. Again, we've got 2 equations. I'll label them 1 and 2 here, so I can just use those to label them on the xy plot. And the first gap here in the y equals form, y equals mx plus b. Well, the m is +3/2. Okay, that means it's a positive slope. It'll be going uphill. And the b here is +1. So, okay, here we go. There's our b +1 for the first equation. Now remember, this guy equals rise over run. Well, the run is the bottom, +2. The rise is the top, +3. So I always like to do the run first. +2, it goes right here. So here's the run equals +2. Okay, now the rise has got to be +3. So at the end of that first arrow, I got to go up 1, 2, 3. The second arrow goes right here, and that's the rise equals +3. Okay, well, at the end of that second arrow, as you remember from your grafting, okay, that is another point on the line. So just get your ruler out and connect these guys up. And there is the graph of equation number 1. Now, equation number 2, remember, if there's one of the variables missing, then it's real easy to graph this. Okay, we don't have any y's. The only requirement we have is that x equals 2. Well, x equals 2 is right here. Okay, and we draw a line perpendicular to the x-axis at x equals 2. Here it is. Okay, this would be line number 2. Double check this. Is it true that every point in this line has x equals +2? Yeah, okay, so it's correct. Well, here's where they cross right here. And this is our, again, system solution. Okay. Okay, there it is. Okay, let's take a look at another one. So far, both of these have been cases where the lines cross and we had good solutions. Let's see what we got next here. Okay, Now, what's going on here is that we've got two equations, but we got to work on these a little bit to be able to solve them. Neither one of them is cleanly in the y equals form. Now, notice that the second guy, the x and y on the left, the plain number on the right, that's the primo form for using intercepts to solve it. So I'll take this first guy and just set him up. I'm going to either have to solve him for y equals or put him in standard form. I'll put him in standard form. I'll take this minus 5x and jump it over. So here's what we have first here. This will go over as positive 5x. You could put a plus in front if you wanted. Then we have plus 5y equals 10. Okay, well now, to be able to solve this easier, there's a common 5 we can divide out, so let's do that. 5 and 5 and 5. Remember, you can divide every term as long as you do it once and only once to each term on both sides. Well, the 5's cancel out here, and 5 goes once here, and a 10 it goes twice. So what we really have for this first equation, once we've cleaned it up, and I just decided to put it in standard form. You could have done it in slope-intercept y equals form if you want. But I've got x plus y equals 2. Now, look at what just happened here. You see the second guy? The second guy is also x plus y equals 2. This is going to be the case where the two lines are on top of each other. Now, let's go back and plot the first guy. The x-intercept equals, and the y-intercept equals. Remember, when you do the intercept methods, if you're after the x-intercept, the other guy is always 0. So if y is 0, x equals 2. And going after the y-intercept, x is 0, y is also 2. So for the first equation, x equals 2, here it is. Y equals 2, here it is. Remember now, these are the intercept points where the line intercepts the x-axis and the y-axis. And so now just get your ruler out here and connect these guys up, okay, about like so. So this is equation number 1. Well, notice equation number 2, since it's the same thing, is going to have the same x and y intercepts. So if I go to plot equation number 2, here's what's going to happen. I get x equal plus 2, y equal plus 2, and I go on top of this and I get exactly the same line. So here's an example of a case where you've got the two lines the same. Didn't look like that to begin with, but once you simplified it, you could see that the first guy was exactly the same as the second. Okay, well that means then that all the solutions along this line are possible answers, each x and y. And so that means we've got infinite solutions. If this was supposed to be equations from a real problem, you've definitely made a mistake someplace here, because you've got an unlimited number of solutions. Which one is the one for your particular problem? You can't tell. Okay, so this is one of these bad cases. And again, the bad cases come from the equations. Doesn't make any difference what solution method you use. When you're bad, you're bad. Okay, now let's look at one last guy here. Okay, here we go. Once again, we've got a potential system right here. And what we want to do is graph both of these guys on the single grid that we got here and see what happens. Okay, well, what I'm going to have to do with these is solve them. Well, let's see. We got the x and y's on the left on both of these. So we could use intercepts. Let's go ahead and do that. So x-intercept equals, remember you set y equal to 0. So we get 3x equals 1. You divide both sides by 3. X equals 1/3. Okay. The y-intercept equals, well, okay, remember this is when you set the x equal to 0. So negative y equals 1. You divide both sides by negative 1. You get y equal to negative 1. Okay, here's our first graph line then. X equals 1/3. Well, this is x equals 1. 1/3 would be about 1/3 of the way there, so I'll put a dot right about there. X equals 1/3. Now remember, these are intercepts where they cross the xy axis. The y now is -1. That's right here. So here's my x-intercept. Here's my y-intercept. Now let's go ahead and draw the line through these guys. And this is the graph of line number 1. Okay, let's see what line number 2 does. It's in standard form also, so we can turn around and find the intercepts for it just as well. X-intercept equals, well, okay. Remember, if you're going after the x-intercept, y is 0, so I can cover up the y here. Since it's 0, it's like it's not there. Divide both sides by 3 here, because I want to get what x is. So I get -4/3. Now, this is good to change to a mixed number. 3 goes into 4 once, so this is going to be -1, and there's one part left over. That makes it a little bit easier for us to see where to graph it. It's going to be at -1 1/3. Okay, the y-intercept. Okay, what's it going to be? Well, if we do the y-intercept, we set x equal to 0. So I got -y equals -4. If I divide both sides by -1 to get y positive, then it looks like y equals 4. Okay, here we go. Let's see what happens. We've got x equal to -1 1/3. 1 1/3, and it's negative. So here's 1, and -1/3 would be about there. Remember, -1 1/3. The y-intercept is 4. Okay, 2, 4. Here it is right here. Okay, now let's see what happens when we graph these guys up. Okay, here it is. My line's a little wiggly, but this is number 2. Kind of looks like these guys might be the parallel case. Okay, so if they are indeed parallel to each other, then that means that there is no solution because they do not cross. And if they do not cross, that of course means that officially what we have is no solution. Okay, this is another one of these bad cases. Okay, and if this was equations that you got from a real problem, you goofed up. Okay, you better go back and check the equations because remember, real problems have real answers, and you always get the cases where the two lines cross in one point, and we've seen that in a couple of our examples. But if they're on top of each other or parallel to each other, then that's one of those bad cases. Okay, well, this is how you dust off your graphing skills here to be able to figure out what happens to systems of equations by graphing.